Okay. We are going to continue talking about chapter 14, so continuing to talk about acids and bases and their equilibrium. Let me share the PowerPoint. Okay. So we ended on, let's go back one slide. We ended calculating equilibrium concentrations for weak acids using the Ka. So that expression is at the bottom. Ka equals the products over the reactants. So in a weak acid equilibrium, it would equal H3O plus concentration hydronium ion times the conjugate base. So in this case, Cn minus divided by the concentration of the acid. So this is just a flow chart. It might be useful to you. We'll use these ideas as we work problems. I don't necessarily use this flow chart directly, but you might find it useful. So as you're looking at these equilibria, let me see if I can move this. There's something covering it for me. You're going to start out by listing all the species that could be acids or bases, and then write all the balanced equations for the possible proton transfer reactions. So essentially look at which acids and which bases do you have, and then what reactions could they undergo. Then you're going to identify the principal reaction, the reaction that has the largest equilibrium constant. That'll be something we have to really think about as we go through this process. That might be a harder thing for you to gain intuition. And then you're going to make a table and list the values for each of the species involved. So you're in the principal reactions, so their initial concentrations, how they change, and then the equilibrium concentration. And you always want to define your X as the concentration of the acid that dissociates. That will just make it easy to solve the problem. You're going to substitute the equilibrium concentrations into the equilibrium equation for the principal reaction and solve for X. Calculate the big concentrations, the concentrations of the species involved in the principal reactions. I think this will make a lot more sense when we talk about polyprotic acids. Use the big concentrations and the equilibrium equations for the subsidiary reactions to calculate the small concentrations, the concentration of the species involved in those other equilibrium, and then finally calculate the pH. So you might find this flow chart useful, but I think as we go through the process, it will just be logical. So this is not a new concept, really. It's just thinking about it a little more. So we want to think about the percent dissociation of an acid. So that's essentially telling you how much of the acid that you put in is going to go on and make H3O plus. So that would be the amount of HA that dissociated divided by what you put in times 100. And what you see is that the percent dissociation is going to decrease as the concentration goes up. So when we look at our equilibrium expression, that will make sense. So this is really where that flow chart is going to be useful. When you have a polyprotic acid, that's an acid that has more than one hydrogen on it that can make an acid. So carbonic acid, H2CO3, in the top reaction is a polyprotic acid. Both of those hydrogens can act like acidic protons. So you write the equilibrium expression. So this flow chart says write the equilibrium expression for each possible proton transfer. So the first one is just for the reaction, the first reaction, and that would be Ka1. But then you also have the possibility, once you make HCO3 minus, that's bicarbonate, that can go on and react with water to make more H3O plus, and that's usually given the symbol Ka2, so the equilibrium constant for the second acid dissociating. So now, but you write it exactly the same. So there's no new idea here. It's just equilibrium. So we can write the equilibrium expression for that second proton coming off, our products over reactants. These are some of the acids that are polyprotic. And you would know this because in the table, you'll have more than one Ka. So if I give you a table of Ka values, if for a particular acid you have 2, then you know that it has 2 acidic protons. In this case, phosphoric acid has 3, so that means it has 3 protons that can act like acids. Notice that the Ka's always get smaller, so the first proton comes off easier, then the second one comes off harder, and the third one usually has a very, very small Ka. So when we're dealing with polyprotic acids, the first dissociation, because that's the biggest equilibrium constant. So for example, for carbonic acid, 10 to the minus 7 versus 10 to the minus 11 for the first and second proton. So that'll be the most important reaction. It has the largest Ka. So we're going to do what the flow chart said. We're going to write the concentrations we started with. How do they change as a function of X? And then what are they at equilibrium? And we're going to put those values into Ka1. So we put them into Ka1 and we find out that from that first reaction, the hydronium cation's concentration is 9.3 times 10 to the minus 5, which would make the pH of the solution about 4.03. So they should have gone into why you didn't deal with the second proton. You'll see that when you look at how the second proton comes off with a much smaller Ka, it doesn't significantly change the hydronium ion concentration. So the pHs really depend on that first proton. We'll do more problems like that in class. So if we have weak bases, it's going to be the same equilibrium concept, but now we're going to use a Kb. So we call it the equilibrium constant for the base reacting in water. So in this case, the base is B, water acts as an acid. The conjugate base is going to have picked up a proton, so it'll be BH plus, and then water has given up that proton, so now it's a base. So the base dissociation constant is just an equilibrium constant for this type of reaction where a base is dissociating in water. So it's products over reactants. Liquid water is left out because its concentration is constant. So you can write the expression. So if you have a specific reaction, you could have written it for the generic reaction above, but they're showing you that for ammonia, NH3, it acts like a weak base. And so you're going to end up with products over reactants, just like any other equilibrium expression. These are some Kb's for weak bases. And you can look at the conjugate acid. And if you have a fairly strong weak base, the conjugate acid is going to be super weak and vice versa. So this isn't a new concept. So now we just have a reaction that's not an acid, but it's a base. So you write out that reaction. You look at how the concentration changes from what you put in, and then what it is at equilibrium. You put those values into the Kb expression. You solve for X, but now remember X is going to be equal to the OH minus concentration, not the H3O plus concentration. So if you want the pH, you have to find H3O plus using Kw over OH minus. Where's my pointer? There it is. So Kw over OH minus gives you the H3O plus, and then you can get the pH as we've done it all along. pH is equal to the negative log of the hydronium ion concentration. So when you look at it, if you have a Ka for a base, you can always, or for an acid, you can always get the Kb for the conjugate base. So this shows you that if you have NH4 plus, which is a weak acid, and you write its expression for dissociating in water, that would be a Ka. Then if you look at the conjugate base, so the NH3, which is the product from the first reaction, NH3 is a weak base, so it reacts in water to make that conjugate acid again. And so that second reaction would be a base dissociation reaction. If you add those two together, you get the Kw for water. So if you add those two together, things cancel from product and reactant side. And so if you add them together, what you see is that the Kw, therefore, has to be the product of the Ka times the Kb for those two reactions. So here's the expression for Ka for a weak yeah, a weak acid, the Kb for a weak base. If you multiply those together, everything cancels and you get the expression for Kw. And so if you know Ka or Kb, you can solve for the other one by knowing that their product has to equal Kw, the dissociation equilibrium constant for water. So Ka times Kb equals Kw. It's only true for a conjugate acid-base pair. So that allows you to always determine the Ka or the Kb if you have the other one. And this just reminds you, you can take a P of anything. So if you take P of both sides of that equation, it also shows you that pKa plus pKb has to equal pKw, and that has to equal 14. So if you think about it, every time something dissolves, it could act as an acid or a base, depending on its properties in water. So when we look at salts, and some of them yield neutral solutions, but some will yield acidic or basic solutions. So the ones that will yield neutral solutions are cations from strong bases. So if you think about it, if lithium hydroxide, for example, is a strong base, that means it all dissociates. So that means if you put lithium plus into water, it's not going to pick up an OH minus because it likes to dissociate. It's a strong base. Same thing is true of the alkaline earth metals. They're strong bases, so they're not going to act like acids or bases. They'll be neutral. So anions from strong monoprotic acid. So if you have a strong acid, something like HCl, when you put it in water, all of it dissociates to make hydronium ions and Cl minus. So that's the same thing as saying if you put Cl minus into water, it's not going to react with water to go backwards to form HCl. It likes to be, the H likes to be taken off of it in water. So if you have a salt that yields an acidic solution, you must be making a weak acid. So something like ammonium chloride, NH4Cl, when it dissociates or when it dissolves in water, you get NH4 plus and Cl minus. And if you look at a table of weak acids and bases, you'll determine that NH4 plus is a weak acid. Therefore, if you put ammonium chloride into water, it's going to be slightly acidic. Salts that yield acidic solutions. So this was one of them. And this is another one. So this is a function of the concept of a Lewis acid, which these slides haven't talked about yet. Yeah, you really need to understand the idea of a Lewis acid and a Lewis base to understand that slide. So we will skip over this one right here. And then we'll come back to it when we talk about Lewis acids and bases. So salts that yield basic solutions are just going to be the opposite. So something like sodium cyanide, NaCl. We know if we look, let's look all the way back at our Ka table, I think. Here. So this says that HCN is a weak acid. Therefore, if you put Cn minus into water, there, if you put Cn minus into water and you know that HCN is a weak acid, that means that Cn minus is a weak base. So if you dissolve sodium cyanide, which produces Cn minus in water, you're essentially putting a weak base into water. If you have both, like if you put into water a cation and an anion, and one of them is an acid and one of them is a base, then in order to decide which is which, it will be true that the one with the larger equilibrium constant will change the pH the most. So if Ka is greater than Kb, the solution will have an excess of H3O plus. So that means it's more acidic than the other one is basic. And if Ka is smaller than Kb, the solution will have a stronger weak base in it, so it will be a pH greater than 7, so that means it's going to be a base. And if they're about equal, the solution will be pretty neutral, pH of 7. Okay. So this is just showing you how you get the values in order to make the decision. So for NH4 plus, so if we dissolve ammonium carbonate, NH4, 2 of those with a carbonate, you have to look at the relative acidity of the NH4 plus compared to the relative basicity of the carbonate, the CO3 2 minus. So we have a Ka for NH4 plus, and we get it by knowing the Kb from the table for the conjugate base. And so the Ka for NH4 plus is 5.6 times 10 to the minus 10. But if we look at the Kb, in order to get the Kb, we need to look at the Ka for HCO3 because that's given in the table. And we come up with the Kb for carbonate being 1.8 times 10 to the minus 4. So that says that it's a NH4 is a weaker acid than carbonate is a base. And so if carbonate's a stronger base than ammonium is an acid, then this is going to be a basic solution. This is just summarizing what each of these slides went through. So I think it's a good summary and you can think about why each of those is true. So I think the last thing we do in this chapter is give another even more general definition of an acid and a base. So the Arrhenius definition is very specific. Acids are things that dissociate to give H plus. Bases are things that dissociate to give OH minus. Bronsted-Lowry is that you can produce H plus in water or you can produce OH minus, but they don't necessarily dissociate to make those. So a Lewis acid is very general. It's an electron pair acceptor, and a Lewis base is an electron pair donor. So things like ammonia, which were Lewis bases in the Bronsted-Lowry definition, are also Lewis bases here, but now you can see why. NH3 has a lone pair on it, and in order to pick up that proton, it donates its lone pair to the proton. So a Lewis base, an electron pair donor. This is also a Bronsted-Lowry base, but it would not be an Arrhenius base because it doesn't dissociate in water to make OH minus. So this is just showing you some other examples of Lewis acids and bases. So NH3 is a base. A Lewis acid would be something like copper 2 plus. It can accept those 2 electrons, and when it does, it forms copper complex to 4 NH3s. And this is just showing you more examples of how that idea that a base is something that donates electrons and an acid is something that can accept an electron pair. And so when we go back, let's go back to that slide, this one. So here you have water. It's not this is actually creating a reaction. So now you have water. The electrons are attracted from water onto the aluminum 3 plus because it has a +3 charge, and that weakens the OH minus bond. If you weaken the OH minus bond, then you're going to pull off a proton and make water into H3O plus. So I won't ask you to do any problems with Lewis acids and bases, but just to understand the concept that it's a much more general definition of what an acid and a base are. Electron donors and electron pair donors and electron pair acceptors. Okay, so we are done with just basically defining acids, bases, getting a better understanding of terminology, things like pH, and then looking at equilibrium. And the next chapter, we're going to go into a few more applications of acid-base equilibrium, things like buffers, which are super important. And we'll do that in another lecture.